think about how a capacitor discharges. So let's imagine that we've got a charged capacitor. So the capacitor is positive charge and negative charge. And I want to discharge the capacitor. So we're going to discharge through a resistor. Now, the bigger the resistance, when I close the switch, the less current flows. And the less current that flows, then the slower the capacitor discharges. The smaller the resistor, the faster the discharge rate. And so there ought to be some way of figuring out what's happening. Well, we know that we can imagine doing a Kirkhof loop. Okay, so we got some current flowing here when I close the switch. Okay, so if I do a single Kirkhof loop, now remember I said this works for all problems. So a single Kirkhof loop going clockwise here, I increase across the capacitor, so that's positive voltage of the capacitor, okay, and then I decrease across the resistor minus IR, and that's going to equal 0. Okay, so what's the voltage on the capacitor? The voltage on the capacitor is going to be Q over C minus IR equals 0. Okay. Well, what is I? I is the rate of change of the current. Okay. Now, the thing is, the rate of change of the current is actually, we want to have a positive IR, so positive current, but dQ dt is negative because we're discharging. So in order for the math to work out, for the current to be positive, we got to define I to be minus dQ dt, because I is going to be the dQ dt through the resistor. So I in the resistor is going to be minus dQ dt, where Q is the Q on the capacitor. Okay. So that means we could say Q over C plus dQ dt R equals 0. Well, let me move that to the other side of the equation here. So we have dQ dt equals 1 over RC times Q. And that would be negative if I move to the other side of the equation. Okay, now I want to solve this equation. This is a differential equation. Now, how do you solve a differential equation? Well, what you do is you do lucky guessing. Okay, what you do is you imagine you ignore this part right here at first. And you say, what can I think of if I take a derivative, I get what I start with? Well, that'd be like an exponential function. What can I think of as a derivative? I get negative from what I start with. That would be e to the negative something. Does it make sense? So, so the derivative, d dt of e to the minus ax equals minus a e to the minus ax. Okay, well, that right there is going to be the 1 over RC. So I would say, therefore, that Q is going to be some Q naught e to the minus 1 over RC times time. So there's my discharge rate of the capacitor. There's the Q on the capacitor. If I want to know the current in the capacitor, then the current, that's going to be dQ dt, and so the rate of discharge is going to be equal to minus Q naught over RC e to the minus 1 over RCT. Okay, so what does this mean? This means that our capacitor starts at some Q naught, and if you graph that versus time, it drops like that. Now, we know that the voltage on the capacitor is Q over C, so we could then say that the voltage on the capacitor versus time is an exponential drop. Okay, so now that doesn't mean it actually ever goes to 0. It drops very quickly, but as time passes, it's asymptotically approaching 0. So if you have a big enough capacitor, and a big enough resistance, it could take a very long time to drop to zero. And so this is sometimes a problem with people using high voltage circuits, is that they think the capacitor is discharged. They might put a screwdriver or something across the terminals, they get a big spark, and they think they discharged it. What they did was it dropped it there to there. Okay, remember, it takes a time, and so it may have dropped it from 10,000 volts down to only 1,000 volts. Well, that's still potentially very bad for you. Okay, and so capacitors often will maintain a dangerous amount of charge on them. Okay, so this is the discharge capacitor. Q naught e to the minus 1 over RCT. Well, we can also write that e to the minus t over RC. Okay, and so we know that the exponent has to be unitless. So that means that R times C has to have units of time. Well, does it? We got an ohm farad. Okay. All right. So what is an ohm farad? Well, a farad is a coulomb per volt. Okay. And an ohm is a volt per amp. Okay, but an amp is a coulomb per second. So that means this is a volt second per coulomb times coulomb over volt. So everything cancels, that's units of seconds. So an ohm farad is just a weird way of writing a second. Okay, so that means the quantity R times C has units of time. So we often call that a time constant. And the symbol we use for time constant is a lowercase Greek tau. So sometimes you will see Q equals Q naught e to the minus t over tau, okay, where tau is known to be RC. Okay, so what does the time constant tell you? It means if t equals 1 tau, so in other words, if t equals R times C, that means that the Q is now dropped, because now it's going to be Q naught e to the minus 1. So that means it's going to be 1 over e. So that's going to be lower. It's not 0. Okay. What if t equals 2 tau? So it's 2 times RC. That means Q is going to be equal to Q naught e to the minus 2. Okay. All right. So now what is 1 over E? Okay. So 1 over E turns out to be, so 1 over E, that's e to the minus 1. Okay, that's equal to 0.368. So that means that after one time constant, then you are 36.8% of the original. Okay. But after two time constants, you're 36.8% of the 38.6. So that's going to be 0.135. Okay, so it doesn't drop linearly, it drops in this fashion asymptotically. So that's an introduction now to discharging of capacitors.